Okay, welcome back once again to the tutorial about the chemical applications of group theory. And this is the 11th video in the application part of group theory. And in the last two videos we had been discussed about molecular orbital theory. In the first video we discussed about the projection operator, symmetry adapted linear combinations. And in the second video, we discussed about the introduction of molecular orbital theory. What are the basic concepts? And in this video, we are going to discuss about the application of molecular orbital theory, taking a specific example. That is, here we are going to discuss about molecular orbital treatment of water molecule. Okay, listen. We know that water molecule belongs to C2V point group. That all we know. And the molecule is placed in the YZ plane. And this is the Z axis, this is Y axis, and this is X axis. So molecule is placed in the YZ plane. And that is C2 axis coincide with Z. That is C2 is actually Z axis itself. Actually it is C2Z. And sigma V XZ plane is sigma V is the XZ plane, and that is this plane sigma V, and sigma V dash is the YZ plane. Sigma V dash is this plane. Okay, we can see like this. This is a sigma V YZ plane. Okay, and that we already know. Then molecular orbital treatment of water involves devising a means of working out which orbitals of its pendant atoms have the same symmetry. We know that there is molecular orbitals are formed by the linear combination of atomic orbitals. So the combining atomic orbitals of the central atom and the pendant atom. What do you mean by a pendant atom? What is a pendant atom means? Pendant atom means the atom, pendant actually means hanging. Okay, pendant atom means the atoms attached to the central atom. That is pendant atom. In the case of this case of water molecule, these hydrogens are the pendant atoms. So the combining atomic orbital should have same symmetry. That is one of the basic principle of molecular orbital theory. Okay, so atomic orbitals of oxygen, that we know we can find out the symmetries, and the combining atomic orbitals of hydrogens should have same symmetry. So we are working out which orbitals of its pendant atom have the same symmetry. Okay, and in the first step in the molecular orbital treatment, the first step is identifying atomic orbitals involved. What are the atomic orbitals involved in the combination? Among atomic orbitals of water, the minimal basis set involves, in the case of oxygen, 1s, 2s, 2px, 2py, 2pz orbitals of oxygen, and 1sa and 1sb orbitals of two hydrogens. That are the minimal atomic orbitals or minimal basis set. Okay, we shall consider those of the central oxygen atoms separately from the set of two 1s orbital hydrogen atom. We are considering orbitals of oxygen and orbitals of two hydrogens, pendant hydrogen atoms are separately. Okay. Now we want to find out what are the symmetry species of the orbitals of the central oxygen atom. Okay. The central atom has a unique distinction from other atoms, that it lies on all the symmetry operation of the molecule. Like in the case of water molecule, oxygen is the central atom and all symmetry elements passing through this oxygen. So it is unique. This means that all atomic orbitals of oxygen are transformed as any of the IRs of the group. Okay, since all symmetry elements passing through the central atom, so all the atomic orbitals of the central atom involves any one of the IRs of the group, irreducible representations of the group. Okay. Okay, in the case of oxygen, it belongs to C2V point group that we know. The 1s, 2s orbitals and 2pz orbital transforms as the characters are 1 1 1 1. Okay, that is 1s orbital, we know it is spherically symmetrical. So C2 the character will be 1 and E character will be 1, C2 character will be 1, sigma V xz character will be 1 and sigma V yz also character will be 1. As in the case of 2pz orbitals also, this is 2pz orbital plus minus here. Okay, 2pz is not like this. 2pz is on the z axis. Plus minus. Sorry, it is minus here. So, this is the C2 axis. On rotation, no change. Therefore, character will be 1. And sigma V xz is passing through the middle of this orbital. Character will be again 1. And sigma V yz also, this is the plane. Plane of the orbital itself. There will be no change on the sign of the lobes. So, character will be again 1. So, it belongs to, that is 1s, 2s and 2pz belongs to A1 representation. Okay. Because character 1, 1, 1, 1 means A1. Okay, it is A1. And another way, we know that all s orbital transforms as A1. That is, we all already studied that all s orbital transforms as totally symmetric representation. Okay, all s orbital is the basis of the totally symmetric representation, that is A1. And 2pz also here also z coordinate. Okay, z coordinate and 2pz orbital transform similarly. Okay, we know that z coordinate and 2pz orbital transform similarly. Therefore, z belongs to A1. So, 2pz belongs to A1. And 2px, okay, we can consider 2px orbital. Okay, 2px orbital. Suppose this is the x-axis, plus minus here. This is z-axis. This is y-axis. This is x-axis. So C2 is in between these the lobes. Therefore, sign changes. Therefore, it is minus 1. Okay, and sigma V xz passing through this one, there will be no change. Therefore, this is 1. And sigma V yz cutting this yz plane, cutting plus and minus lobes. The center of the plus and minus lobe. Therefore, plus and minus interchange. Therefore, it is minus 1. So 1 minus 1, 1 minus 1. Where is that? The 1 minus 1, 1 minus 1. So it belongs to B1 representation. So 2px belongs to B1 representation. Or in another way, we know that the 2px orbital transforms same as that of x coordinate x. Okay. Okay, here x transforms as B1. So 2px belongs to B1 representation. And next 2py. This is 2py orbital. We can draw here 2py orbital. This is xyz axis. This is a 2py. This is a y axis. This is x. This is z axis. And here plus sign, here minus sign. Okay. So on C2 rotation, the lobes interchanges. Therefore, sign will be minus 1. Sorry, here minus 1. And sigma v xz, sigma y is xz passing the middle of the plane. Therefore, plus and minus interchanges, again minus 1. And sigma v yz is this plane. No change in the sign. Therefore, this 1. So 1 minus 1 minus 1 1. What is that? 1 minus 1 minus 1 1. It belongs to B2. B2 representation. So 2py symmetry B2. Or another way we can easily find out from the character table itself, because the coordinate y transforms similarly as 2py orbital. It belongs to B2. Okay. So 1s, 2s and 2pz has a symmetry of A1 symmetry. 2px B1 symmetry, 2py B2 symmetry. These are the atomic orbitals of oxygen. Okay, it belongs to the symmetry species A1, B1 and B2. Clear? Now, okay, now the third step is creating group orbitals from the pendant hydrogen orbitals. Symmetry adapted linear combinations. Okay, now we got the symmetries of the central atom. Now we want to take the group orbitals from the hydrogen orbitals. Okay, that is the two pendant hydrogen atoms do not lie on all of the symmetry species, symmetry elements of the molecule. That is, in the case of water molecule, oxygen passing through all the elements passing through oxygen. But in the case of hydrogen, all the symmetry elements not passing through or any of the hydrogen atom. Okay, so neither of the oneness orbital of two hydrogen atoms can therefore transform as any of the IRs of the C2V group. Okay, that is, in the case of this hydrogen, all the symmetry elements not passing through this hydrogen and this hydrogen. So they do not belong to any of the IRs of the C2V point group. Okay. The hydrogen orbitals thus do not reflect the symmetry properties of the molecule. Hydrogen orbitals do not reflect the symmetry properties of the molecule and hence cannot be used directly for the construction of MOs of the molecule. Okay, these two 1s A and 1s B orbitals of hydrogen, hydrogen A and hydrogen B, cannot be used directly for the construction of molecular orbitals because they do not belong to the IRs of the group. They do not belong to the same symmetry of the central atom. So we have to, the general method is, generally the MO treatment of MXN type polyatomic molecule, the relevant orbitals of pendant atoms are considered as a group. Okay, that is, orbitals of the pendant atoms are considered as a group and their various linear combinations are considered. Okay, we are not using directly the orbitals of pendant atom. We are considering there's various linear combination and that is called the symmetry adapted linear combinations of the pendant atoms. The resultant combinations are referred to as group orbitals. Okay, and there are several methods to find out the symmetry adapted linear combination, but one of the easiest and systematic method is projection operator method to find out the SALCs of the pendant hydrogen atoms. Okay, projection operator. That is a systematic and scientific way. And before discussing about the projection operator, we already discussed in the first video. Before directly going to projection operator, there are some direct method to find out the symmetry adapted linear combination. Okay, first we want to go and discuss about that methods. Then finally we move towards the projection operator technique. Okay, can you follow me? That is the we get the symmetries of the central atom, and this atomic orbital central atom should have to combine with the atomic orbitals of the pendant atoms or combining atoms. But there is a problem. That is, these pendant atoms do not belong to the IRs of the group. They do not transform all the any of the symmetry of the point group. So we cannot use directly the orbitals of the pendant atom. We have to consider that as a group and we can form a symmetry adapted linear combination. And symmetry adapted linear combination easily obtained from the projection operator technique. And before going to the projection operator technique directly, there are some other methods, direct methods to find out the symmetry adapted linear combination. Okay, then, okay, that is, in the MO treatment of water, we consider the linear combination of two hydrogen 1s atomic orbitals. Only two linear combinations are possible directly because we have only two orbitals, SA and SB. Only two combinations are possible, SA plus SB and SA minus SB. This is SA plus SB denoted as Psi1 and SA minus SB denoted as Psi2. In order to know the symmetry species of the above SALCs, There are several methods. We want to know which symmetry species this orbital belongs. That can be determined by group projection operator easily, and before that there are some other technique to find out the symmetry properties of these SALCs. First method is, this is the first method. First method is to consider the effect of symmetry operations on psi1 and psi2 directly. Okay, that is psi1 is SA plus SB. Okay, SA plus SB is psi1 and psi2 is SA minus SB. Okay, so on E operation SA plus SB remains same, no problem. On C2, that is, this is the picture. This is SA plus sign is here. This is SB. This is also plus sign because this is psi1 SA plus SB. So on C2 operation, SA and SB interchange, but there is no change in sign. Here also plus, here also plus. Therefore, the character will be 1. And sigma v xz also, as xz case, this is the xz plane, but here plus, here also plus sign. Therefore, again character 1. Sigma v yz is this plane, here also 1. Therefore, in the case of psi1, that is psi a SA plus SB, that is a psi1. Gamma psi1 is equal to, that is characters is equal to 1, 1, 1, 1. That is belongs to A1. That is, this SA plus SB belongs to, okay, SA plus SB belongs to A1 symmetry, A1. Okay, then psi2, SA minus SB. In picture can be drawn like this. Okay, this is oxygen. This is SA, here plus sign. This is SB, but here it is minus sign. Here it is plus, here it is minus, because it is SA minus SB. So minus of plus, already S orbital is plus sign, so minus of plus is, it is minus here. Therefore, by E operation there will be no change, okay, but C2 operation plus and minus interchange. Here minus, here plus. By C2 operation SA and SB interchanges, so plus become minus, minus become plus. Therefore, it is minus 1. And sigma v xz is, sorry, okay, sigma v xz plane is this one. Here also plus and minus interchanges, therefore character is minus 1. And sigma v yz plane is this molecular plane. No change in the sign, therefore it is 1. Okay, so characters are 1, minus 1, minus 1, 1. We go back to the character table, we can see that it is B2 symmetry. Therefore, psi2, that is SA minus SB belongs to B2 symmetry. Okay, B2. Okay, so SALC psi1 belongs to A1 and SALC psi2 belongs to B2. This is the first method. Okay, in this case, this is very easy because there are only 2 orbitals, 2 combinations are possible. But in the most cases, if you have a larger number of orbital, it is not easy to find out the symmetry species in this way. Okay, another method, second method. Another method is to find out the symmetry of the SALCs, is to consider the symmetry operation on the 2 atomic orbitals and generate a reducible representation. Okay, first, this is our orbital, 1SA, 1SB, here plus sign, here it is plus sign. Okay, and we know that we consider these two both together. Therefore, during a symmetry operation, we have studied that if position of orbital changes, they do not contribute to the character. Only the orbital which remains, which position retained, will contribute to the character of the reducible representation. Okay, and we know that during E operation, no change in the position of this 1s and 1sb. Therefore, character will be 2. 2 orbital do not change position. During symmetry operation, C2 operation, both 1s and 1sb changes their position, character will be 0. And sigma v xz is this plane, here also position interchanges, no contribution. But in the case of sigma v yz, okay, this is the plane, molecular plane, 1s and 1sb remain stationary, no change in their position, and no change in their sign also, therefore it is 2. Okay, clear. This is the reducible representation 2, 0, 0, 0, 2. And this one reduction. I am not going to explain the reduction method. We have all discussed many times how a reducible representation can be reduced into irreducible representation by reduction formula. I think you remember the reduction formula and all these things. Then we get, on reduction we get, it belongs to A1 plus B2. This is the second method. This also possible in this case very easy, because only 2 combinations are possible, 2 atomic orbitals are there. But if there are more number of orbitals, this method is also somewhat difficult. And third method, that is the most easiest and systematic method, using projection operator. To determine the SALCs and their symmetry, the most systematic and universally applicable method is projection operator method. And we have already discussed about the projection operator in the first video. If you forget this projection operator, what is projection operator on this, please watch the video for molecular orbital theory part 1 video once again. Okay. And projection operator is one which, when acting on a function, projects out a specific function or a combination which forms the basis for the representation under consideration, and it annihilates or it cancels all other parts which do not form basis for the representation. That is, a projection operator projects. That is, we are putting a function on projection operator having a particular symmetry. Okay, then it projects out only that part of the function or their combination having the same symmetry, and all other part is annihilated or cancelled or eliminated. Okay, and this is the equation for projection operator. P cap gamma I is equal to Li divided by H sigma R chi I R cap, where P is the projection operator of the particular representation, gamma I is a particular representation, Li is the dimension that we know, H is the order of the point group, sigma or sum over all the operation, chi I R character of the operation, into operator R acting on a function. Okay, clear. Then okay, let us apply projector operator for the construction of SALCs from the set of 1s orbitals of the pendant hydrogen atoms on water molecule. We are going to apply projection operator. We have 2 orbitals, 1sa and 1sb. We can take only 1 orbital, 1sa, because the effects will be same for 1sb orbital. We need not take all these orbitals, we take only 1 orbital, 1sa. And if 1sa is subjected to different operation of the C2b point group, we know that on E operation 1sa, Sa become Sa itself. On C2, Sa is converted into Sb. On sigma v, Sa, sigma v xz is this plane converted into Sb. And sigma v yz is this molecular plane, Sa remains as Sa. Okay, this is the change in the wave function, change in the orbital is actually a wave function, change in the orbital by applying the symmetry operation on the Sa orbital. Okay, then yes, now apply projection operator one by one. Pa1 Sa. Okay, that is A1 projection operator on the orbital Sa. So Li is equal to 1. This is a one-dimensional. A1 is a one-dimensional representation. In the case of E2b, all are one-dimensional. All representation are one-dimensional. Therefore, 1 divided by order of the C2b point group is 4 into chi I R, chi I of E, that is 1, into R acting on the function SA. E operator E acting on the function SA. And next C2, the character is 1. C2 operate on the function SA. Again sigma V 1. The operator sigma V XH acting on the function XA, and 1 here, also 1 here, into sigma V dash acting on SA. So 1 into E of SA on SA remains, we know that as this is a change, that is E C2 sigma V dash. Okay, SA remains SA here. Here SA become SB. Here sigma V SA become SB. Sigma V dash SA become SA itself. Okay, that we know. Then E into SA is equal to SA, and C2 SA is equal to SB. So it is SB here. And sigma V SA again SB. SA is converted to SB. Here SB. And sigma V dash SA remains SH. Therefore, it is SA itself. So 1 into SA is equal to SA. So this is equal to 2 SA plus SB. 2 by 4 is cancelled. Therefore, is 1 by 2 into SA plus SB. This on simplification we get 1 by 2 into SA plus SB. Okay, clear. Okay. So the projection operator projection operator A1 acting on the function SA projects out a combination of SA plus SB, that is half SA plus SB. That means the meaning of this is the linear combination SA plus SB has a symmetry of A1 symmetry. Okay, can you follow me? That is, if projection operator A1 acting on the function SA, we get a function SA plus SB, a combination. That means that the linear combination SA plus SB has a symmetry of A1. Okay, because a projection operator projects only that part of the function or their combination having the same symmetry. Therefore, SA plus SB has a symmetry of A1. Then PA to SA. Okay, the A2 representation, A2 symmetry projects on the function SA. Again 1 by 4 into here 1 into ESA. ESA is equal to SA. Okay, then again C2 here 1 is 1 again. Therefore 1 into C2 into SA is equal to SB. So 1 into SB is equal to SB here. Okay. Then here it is minus 1. So minus 1 into sigma V into SA. Sigma V into SA is equal to SB. Sigma V into SA is equal to SB. Therefore minus 1 into SB. So it is minus SB here. Okay. Next again it is also minus 1. So minus 1 into sigma V dash SA. And sigma V dash SA is equal to SA itself. So minus 1 into SA, that is minus SA. So this SA and minus SA cancelled. SB and minus SB cancelled. Therefore 0. So no linear combination having symmetry of A2. No linear combination of SA and SB belongs to A2 symmetry. That is its meaning. Okay. Next PA1. PB1, it is not A1, it is B1. B1 SA. This is third one, B1. Okay, again 1 here. So 1 by 4 into 1 into E into SA is equal to SA. Minus 1 into C2 acting on SA is equal to SB. So minus SB. Next sigma V XZ acting on SA is equal to SB. So it is 1 here. So 1 into SB, again SB here. Third one, character is minus 1 here. Minus 1 into sigma V dash SA is equal to SA. So minus SA. Here also this SA and minus SA cancelled. SB minus SB plus SB cancelled. Again 0. There is no combination having B1 symmetry. No combination of SA and SB. No linear combination of SA and SB belongs to B1 symmetry. That is its meaning. And the last one, that is B2, that is P. It is not A1, it is B2 SA. That is projection operator B2 acting on the function SA. 1 by 4 into again 1 into E into SA is equal to SA. Again minus 1 into C2 into SA is equal to SB. So minus SB. Again minus 1 into sigma V XZ into SA is equal to SB. So minus SB again. And 1 into sigma v dash yz into SA, that is SA itself, therefore 1 into SA. Again SA plus SA, 2SA minus SB minus B minus 2SB, or 2 we can take an outside, 2 by 4 is equal to 1 by 2, so it is 1 by 2 into SA minus SB. Okay, that means the combination SA minus SB belongs to B2 symmetry. Okay, so that is we get only two linear combination, two SALCs, that is 1 by 2 into SA plus SB, that belongs to A1 symmetry, and 1 by 2 into SA minus SB, that belongs to B2 symmetry. Okay, that is our next slide. Okay, that is we see that there are two non-zero result, that is 1 by 2 into SA plus SB, that belongs to A1, BA1, and 1 by 2 SA minus SB, that belongs to B2, showing that LCAOs, SALC atomic orbital psi1 and psi2 belongs to A1 and B2 symmetry respectively. That is psi1 is equal to SA plus SB. Okay, that belongs to A1 symmetry, and psi2, that is SA minus SB, that belongs to B2 symmetry. That is our conclusion. But we have to normalize this function. We can neglect this 1 by 2, this 1 by 2, etc. because we want to normalize this function, then that will be included that normalization. So no need of this 1 by 2. We can neglect this Li divided by S in the initial stage itself, because it is in the final result this is to be normalized, so no need of this Li by H actually. Okay, the function generated from the projection operator has to be normalized, that is sigma psi star psi d tau is equal to 1, and it also should be orthogonal. These functions should be orthogonal, that is psi I psi j d tau should be equal to 0. So we can neglect this factor 1 by 2 or even this Li divided by H itself in the beginning of the, because it will be incorporated automatically in the normalization constant. Okay, so we have to apply normalization. That is psi1 is equal to 1 by, okay, that is the result. Okay, before that, this is the first slide, that is normalization constant n square SA plus SB the whole square d2, that is our psi1 is SA plus SB, that is we are normalizing, that is integral SA plus SB the whole square d tau should be equal to 0. We are multiplying with the normalization constant n and squaring n square. So n square SA plus SB the whole square d tau, that's equal to n square. N square is constant taken outside, integral SA square plus SB square plus 2 SA SB d tau, and that is equal to 1. No, it's not equal to 0, it is equal to 1. Normalization is equal to 1. So integral of SA square, SA is a function, it's a wave function. Integral of SA square is equal to, according to normalization, integral of psi1 star psi1 d tau is equal to 1. That is normalization. So integral of SA square is equal to 1. Integral of SB square is equal to 1. Integral of SA and SB d tau is equal to 0 because they are orthogonal. Okay. Linear combination is orthogonal, normalized. Yes, atomic orbit is also orthogonal and normalized. So this SA itself is normal, therefore integral of SA square is equal to 1. SB itself is normalized, therefore integral of SB square is equal to 1. And SB and SA and SB are orthogonal, therefore integral of SA SB is equal to 0. So we get 2 into n square is equal to 1, that is n is equal to 1 by root 2. Okay, so we can write psi1 is equal to 1 by root 2 into SA plus SB, that is psi1. Okay, next similarly the second psi2 psi2 n square into SA minus SB square d2, that is n square into SA square plus SB square minus 2 SA SB d2, that is equal to 1. Okay, integral of SA square is equal to 1, integral of again SB square is equal to 1, integral of SA SB is equal to orthogonal 0. Again we get 2 n square is equal to 1, n square is equal to 1 by 2, n is equal to 1 by root 2. Therefore we can write psi2 is equal to 1 by root 2 SA minus SB. So we get two normalized SALCs, that is psi1 is equal to 1 by root 2 SA plus SB, psi2 is equal to 1 by root 2 SA minus SB. Okay. What we have discussed yet is that we have first constructed or find out the symmetry of this atomic orbitals of central atom. Then we take the pendant atom, combine together, group. We cannot take any one of the pendant atom because they do not belong to any of the symmetry species. So we take in together the pendant atoms and take their linear combination and find out their symmetries. Okay, that's all we are discussed till now. Now we are going to construct the molecular orbitals. Okay, and that's the final step. That is construction of molecular orbitals. Now the constructed SALCs combines with atomic orbitals of oxygen having same symmetry to form molecular orbitals. They should have same symmetry. Only atomic orbitals and SALCs having same symmetry will combine. And this is our result. Atomic orbitals of oxygen, we had already find out that 1s, 2s and 2pz belongs to A1 symmetry. 2px belongs to B1 symmetry and 2py belongs to B2 symmetry. Okay, clear. Then SALCs psi1 and psi2. Psi1 belongs to A1, that psi1 is SA plus SB, and psi2 belongs to B2, that is SA minus SB. Okay, now we can combine. And before that, molecular orbitals are labeled by lowercase letters. Remember that, corresponding to the symmetry species of atomic orbitals. Molecular orbitals are labeled by lowercase letters corresponding to symmetry species of the atomic orbital symmetry species are A1 and second thing is B2. Therefore, the labeling of molecular orbital will be A1, B2, A2, B2, etc. like that, B1, etc. like that. Okay, clear. Next, hence in water molecule the MOS would be labeled as A1, B1, B2, etc. Like that we are labeling molecular orbitals. That you have to remember. Next, the oneness, this is very important point, Sadhya. The oneness orbital of oxygen, A1 symmetry, okay, belongs to A1 symmetry, has too low energy corresponding to psi1. That is also A1 symmetry and hence cannot overlap effectively with psi1. So it remains non-bonding. That is, these are our orbitals. Oxygen orbital 1s, 2s, 2pz, 2px, 2py, and SALCs of the pendant atom. This is oxygen. And the symmetries are 1s belongs to A1, 2s belongs to A1, 2pz belongs to A1, 2px belongs to 2px, which was 2px, B1. Okay. 2px belongs to B1 and 2py belongs to B2 symmetry. And SALC psi1 is A1 symmetry and SALC psi2 belongs to B2 symmetry. Okay, this is our point. This A1, 1s A1, 2s A1, 2pz A1. This should combine with psi1. Psi1 is A1. But here one problem with 1s is that 1s is a lower energy orbital. It cannot combine with psi1 because it is a higher energy. Energy should have we know that according to postulate of molecular orbital theory, the combining ions should have comparable energy. Atomic orbitals combining should have comparable energy. So this 1s orbital cannot combine with psi1. So they cannot combine even with psi2 because 2 cannot combine because it is B2 symmetry, different symmetry. 1s is A1. It can, if it combine, it should be with psi1. But psi1 and 1s have different energy, so 1s cannot combine with psi1. So it remains as non-bonding and it is denoted as 1A1. And this 1s orbital is non-bonding. It is denoted as 1A1. Okay, remember that point. And next, neither psi1 and psi2, and this is our orbital, oxygen 1s, 2s, 2pz, 2px, 2py. It belongs to A1 symmetry, it is non-bonding, we already discussed. And this 2s also A1, this 2pz also A1, 2px is B1, 2py is B2. Okay, and our SALCs are psi1 that belongs to A1 and psi2 that belongs to B2. That is our result. Now see here, this 2px has B1 symmetry. In which SALC has B1 symmetry? Never. Neither of them has B1 symmetry because psi1 is A1, psi2 is B2. So 2px cannot combine either with psi1 or psi2. Okay, can you follow me? Because the combining atomic orbital should have same symmetry. That is the one important point. So 2px orbital B1 symmetry, but neither SALC, psi1 and psi2 belongs to B1. So this 2px also belongs to, become a non-bonding orbital. It is denoted as 1b1. That is pointed here. Neither psi1, psi2 spans B1 symmetry. 2px orbital which belongs to B1 symmetry remains non-bonded. It is denoted as 1b1. So this is 1s is non-bonded. It is denoted as 1a1. This 2px is non-bonded. It is denoted as 1b1. Now which will combine? Now this 2py B2 symmetry combines with psi2 B2 symmetry. Okay, 2py orbital of oxygen B2 symmetry, psi2 of SALC, that is also B2 symmetry, combined to form two orbital. You know that the number of molecular orbitals formed is equal to number of atomic orbitals combining. That is the postulates of molecular orbital theory. So when two orbitals combine, we get two molecular orbitals. One is bonding, another is anti-bonding. Bonding is lower energy, that you already know. Anti-bonding is higher energy. So they have B2 symmetry. This also B2. They are named as 1b2, that is bonding, and 2b2, that is anti-bonding. Okay, and that is also over. Okay, now remaining is 2s and 2pz. Both have A1 symmetry, almost comparable energy, and psi1. And these three combines together, all together. That is the beauty of molecular orbit theory. In valence bond theory, you cannot think about this type of overlapping. But in molecular orbit theory, three orbitals combine. And when we don't know actually what is the contribution of the interaction of each of these orbit, that we want to determine by calculation, computational calculation. We have to find out the coefficients. But in a qualitative way, we can say these three combine and form three molecular orbital, and all of this belongs to A1 symmetry. They are named as A1. Okay, and they are named as 2. Already one A1 is here. Already one A1 is here. So this denoted as 2A1. One A1 is 1s from 1s orbital. So this is denoted as 2A1, 3A1 and 4A1. Okay, clear? So these are our combination. That is A1 symmetry, oxygen 1s orbit remains non-bonded. It is denoted as 1A1. And orbitals having A1 symmetry, that is oxygen 2s combines with oxygen 2y with psi1 orbit, which belongs to A1 symmetry. So C1 O2s plus C2 O2py plus or minus C3 psi1. Okay, and we get three orbital, 2A1, 3A1 and 4A1. And the orbital belongs to B1 symmetry, that is oxygen 2px orbital remains non-bonded because neither of the SALC belongs to B1 symmetry. So it is denoted as 1b1. And orbitals having B2 symmetry, that is oxygen 2py orbital combines with psi2. So we can try C4 oxygen 2py plus or minus C5 psi2. We get 1b2, 2b2 orbit, molecular orbitals. Okay. Then the energy order. Okay, energy order, of course, 1A1 is the lowest energy. This is from OS, oxygen 1s. And next is the 2s orbital, molecular orbitals formed from 2s orbital, that is 2A1. and that is actually bonding. This 3A1 is non-bonding and this is anti-bonding. So 1A1 is the lowest, then 2A1. Next is the, I think it is this bonding orbital, that is oxygen 2py combined with Psi2, this 1b2 bonding, then 1b2 bonding. Next is this non-bonding 3A1, and this is also non-bonding 1b1. And next anti-bonding, this is anti-bonding 2b2, next 2b2, and this is also anti-bonding 4A1. That is the order of energy, energy of molecular orbitals. And thus these 10 electrons of water, 8 electrons from oxygen and 2 electrons from these 2 hydrogen atom, are arranged in these 5 lowest orbitals as 1A12, 2A12, 2B22, 3A12, 1B12 that are filled, and 2B2 is vacant, and 4A1, that 2 anti-bonding orbitals are vacant. That is their energy distribution, distribution of electron in these molecular orbitals. And this is the pictorial representation. Okay, this is hydrogen pendant orbitals of hydrogen combined linearly to form SALCs. These are actually SALCs. This is Psi1 and this is Psi2. Psi1 and Psi2. Okay. Then listen carefully. This 2s orbital, and 1s orbital is here actually, and that is non-bonded. So should have same energy. That is 1A1. That is also filled. That is not shown here actually. 1A, that is non-bonded. And this 2s orbital, that is having A1 symmetry, combines with Psi1 sigma, that is also A1 symmetry. And this 2pz, this is the red line is 2pz, and this 2pz also A1 symmetry. So this 3 combine. Okay, that is 2pz, this 2pz, and 2s and this Psi1 combines from 3 orbital, 2A1, 3A1 and 4A1, that is here. And 2px orbital, that is this 2px orbital, this is actually this blue line, combines with Psi2. Okay, they form 1b2. Psi2 is actually b2 symmetry. So they form 1b2 and 2b2. Okay, this is 1b2. We can see here it is 1b2. Okay, then listen. This 2py orbital belongs to b1 symmetry, but neither Psi1 or Psi2 belongs to b1. They are a1 and b2, so it remains non-bonded. That is 1b2. So 1b1. That is non-bonded here. Okay. So electrons are distributed 1a12, 2a12, 1b1 by 2, 3a12, and 1b12. Okay, these 2 are anti-bonding, they are vacant. These 4a1 and 2b2 are vacant. Okay, clear. I think the order is different. 4a1 is upper, no? 2b2 lower. I think this picture is some mistake. You may please refer. Okay, what is actually the pictorial representation? Okay, and this about the molecular orbital theory treatment of water. I think you have understand something in this lecture. Okay, to understand more you have to read book. Okay, read the textbook very well and understand more about this concept. Okay, thank you very much.